Welcome to the Deep Dive, the place where we turn massive amounts of source material into crystalline clarity. Today, we're laying the absolute bedrock for organic chemistry, the language, the shapes, and the rules of the game. Our mission is pretty simple. We're giving you the conceptual map, the foundational dictionary you need for basically every organic reaction you're going to encounter from here on out.
Absolutely.
So we're talking molecular representation, naming systems, bonding, isomerism, and, the mechanisms of reactions.
And the whole reason this field is so vast and why you need this dictionary, it all comes down to one atom, carbon.
Right.
It has 4 valence electrons, this unique ability to bond to itself over and over again in chains and rings. And it also bonds easily with hydrogen, oxygen, nitrogen. I mean, it's the architect of millions of compounds.
Okay, so let's unpack this. Let's start at the very beginning. How do chemists even draw and describe these things?
Well, we can probably skip past the really basic stuff, like empirical formulas.
Yeah, let's assume everyone's got that covered. We want to get to the formulas that actually tell us something about the molecule structure.
Exactly. So the molecular formula just gives you the count. Not that useful. The structural formula, like CH3CHCH2, gives you a bit more.
But it's still a bit clunky.
Very clunky. And the displayed formula where you draw every single bond is just too much information. So we jump to the workhorse of organic chemistry, the skeletal formula.
I love the skeletal formula. It's so clean. It forces you to think spatially.
It does.
You just, remove the carbon and hydrogen symbols, and you're left with these zigzag lines.
Right. And you just have to remember that a carbon atom sits at every point and at the end of every line. And you assume there are enough hydrogens attached to give each carbon 4 bonds.
It's pure efficiency. But there's a key rule, isn't there?
A very key rule. Any atom that is not carbon or hydrogen, what we call a heteroatom, like oxygen or a halogen, that has to be drawn in explicitly.
So if you have an alcohol, like butanol,
you have to write in the OH. You can't just imply it. That functional group is way too important.
And then, to show how they actually exist in 3D space, we have the 3D displayed formulae.
Yeah, the wedges and the dashes.
That's the one. So the solid wedge bond means it's, sticking out towards you?
Sticking out of the page toward you. And the dashed line bond is going back away from you into the page.
And that detail becomes so important later, especially when we hit isomerism.
Oh, it's everything. So that's the visual language. Now, how do we classify them? We put them into families or homologous series.
And these families are all defined by their
functional group. The functional group is the reactive part of the molecule. It's the bit that actually does things in a chemical reaction.
Like the CC double bond in an alkene, or the deci-OH in a carboxylic acid.
Exactly. That group determines the molecule's whole chemical personality.
Okay, so how do we name them? There's a system, right? The IUPAC system.
A very logical system, thankfully. It's all based on these stems for the number of carbons. Meth for 1, eth for 2, prop for 3, all the way up to 10 for 10.
And the most important rule, the one that catches everyone out.
It's all about the numbers. First, find the longest continuous carbon chain. That's your stem.
Okay.
Second, you number that chain. And you have to start from the end that gives any side chains or functional groups the lowest possible number.
So you'd call it 2-methylpentane, not 4-methylpentane.
Never 4-methylpentane. You always go for the lowest number. It's not a choice.
And what if you have more than one of the same side group?
You use prefixes. D, tri, tetra, so 2,2,7,3 trimethylpentane. And if you have different side groups, like an ethyl and a methyl group,
Alphabetical order.
Strict alphabetical order, so it would be 3-ethyl-2-methylpentane, ethyl before methyl.
And a quick one on those ring structures, the aryl groups like benzene.
Ah, yeah. With those, if there's only one group attached to the ring, you don't need a number at all because all 6 positions on the ring are identical.
Simplicity wins. Okay, so we can draw them, we can name them. Now, what about their actual shape? This is where it gets really interesting for me.
This is where we move from 2D on paper to 3D reality. It all comes down to carbon's 4 valence electrons and how their bonds repel each other.
Let's start with the simplest type, the single bond.
The single covalent bond is called a sigma bond or sigma bond. It's formed by the direct head-on overlap of orbitals. All the electron density is squished right between the 2 atomic nuclei.
So in a simple alkane like ethane, where a carbon just has 4 of those single sigma bonds, what shape does that force the molecule into?
Well, those 4 pairs of bonding electrons are all negatively charged, so they push each other as far apart as possible. This is called 6p33 hybridisation.
And that results in the classic.
The tetrahedral shape. The bond angles are always 109.5 degrees. If you see 4 single bonds on a carbon, you should instantly think tetrahedral.
But carbon doesn't just make single bonds. It makes double and triple bonds, which introduces something new.
It introduces the pi bond, the pi bond. This is formed by the side-on overlap of orbitals, and it sits above and below the sigma bond.
Okay, so if you have a C-Phi double bond, that's one sigma and one pi bond, how does that change the geometry?
The carbons involved in that double bond become CP22 hybridized. They only form 3 sigma bonds, so those bonds spread out as far as they can in one plane.
Which makes the molecule
Planar, or flat, with bond angles of 120 degrees. See a double bond, think flat.
And the final step, a C-Kg triple bond.
Like an ethene.
That's one sigma bond and 2 pi bonds. The carbons are now CP hybridized, and the geometry becomes as simple as it gets.
It's just a straight line.
It's linear. The atoms all sit in a perfectly straight line. The 2 pi bonds basically form a cylinder of electron density around that sigma bond.
So that link is key. Single bond, CP3 $2 tetrahedral, double bond, CP2 planar, triple bond, CP2 linear.
Master that, and you can predict the shape of almost anything.
Okay, now that we have the 3D shapes down, we can tackle one of the trickiest ideas in organic chemistry, isomerism. Ah, yes, where the molecular formula just isn't enough information.
Right. You could have a formula like C3H6, but that could be propene, which is a straight chain with a double bond.
Or it could be cyclopropane, a little triangle of carbon atoms. Same formula, totally different molecules.
So how do we break down the different types?
We start with structural isomerism. This is where the atoms are actually connected to each other in a different order. There are 3 types to look for.
What's the first one?
Position isomerism. This is simple. The functional group is just in a different place on the carbon chain.
Like moving a bromine atom from the first carbon to the second carbon.
Exactly. But a crucial point here. If you can get from one drawing to another just by rotating around a single CC bond, they are not different isomers. That's just the same molecule wiggling around.
Good point. Okay, what's type 2?
Functional group isomerism. Here, the molecules have completely different functional groups. A formula like C3H80 could be an alcohol, or it could be an ether.
And they would have completely different chemical properties.
Wildly different. And the third type is chain isomerism. This is where the actual carbon skeleton, the backbone, is different.
Like C4H10, it can be a straight chain butane.
Or it can be branched, forming methylpropane. Same formula, different carbon chain.
Okay, so that's all structural isomerism. What's the other major category?
The other category is stereoisomerism. Now, this is a bit more subtle. Here, the connectivity is the same. All the atoms are bonded to the same partners, but they're arranged differently in 3D space.
And the first type of that is geometrical isomerism. You might have heard of it as cis-trans.
That's the one, and it only happens when you have restricted rotation in a molecule.
Most commonly around a CC double bond, right? You can't just spin it.
It's locked in place. Because of that, any groups attached to those carbons are fixed. If they're on the same side of the double bond, we call that the cis isomer.
And if they're on opposite sides?
That's the trans isomer, across from each other.
And then we get to what I think is the most fascinating type, optical isomerism.
This requires something very specific, a chiral center.
Which is a carbon atom that is bonded to 4 completely different atoms or groups.
That's the key, 4 different things. When that happens, the molecule is chiral, and it can exist as a pair of enantiomers.
Which are non-superimposable mirror images, like your left and right hands.
Exactly like your hands. They're mirror images, but you can't lay one perfectly on top of the other. And this isn't just an academic curiosity, is it? The thalidomide disaster was all about this.
Absolutely. One enantiomer was the intended medicine, but its mirror image, its evil twin, caused horrific birth defects. So this stuff has real-world life-or-death consequences.
It really does. And these enantiomers, they have a unique property. They rotate the plane of polarized light.
One rotates it clockwise, the other rotates it by the exact same amount, but anti-clockwise.
And just to add a layer, if a molecule has 2 chiral centers, you don't get 2 optical isomers, you get 4. The complexity increases.
Okay, so that covers the static structures. Let's get into the dynamic part. How do reactions actually happen? How do bonds break?
We call it bond fission. And there are 2 main ways it can happen. The first is called homolytic fission.
Homo meaning the same, so it breaks evenly.
Exactly. The covalent bond snaps, and each atom takes one of the shared electrons. This creates incredibly reactive species called free radicals. We show them with a little dot, like Kiel.
Okay, and the other way?
Is heterolytic fission. Hetero meaning different, This is an uneven break. The more electronegative atom takes both of the shared electrons.
And that creates ions.
It creates ions. This is how you get a positively charged carbon species called a carbocation.
Right. And carbocations are hugely important intermediates in reactions. Their stability is probably one of the most important predictive tools we have.
Absolutely non-negotiable. The stability order is always. Tertiary is more stable than secondary, which is more stable than primary.
Can you break that down? What makes a tertiary one so stable?
It's all about something called the positive inductive effect. The alkyl groups, the carbon chains attached to that positive carbon, are electron donating.
So they sort of push a little bit of their electron density back towards the positive charge.
Think of them like little cushions. They help to spread out and stabilize that positive charge, which the carbon atom is not happy about having.
So a tertiary carbocation has 3 of these alkyl group cushions, making it the most stable. A primary only has 1.
And that makes it the most unstable and least likely to form. This principle will decide the outcome of many, many reactions.
Before we list the reaction types, 2 last key terms: electrophile and nucleophile.
Yes. An electrophile is an electron lover. It's an electron-deficient species, usually with a positive charge, that accepts an electron pair.
It's looking for electrons. And a nucleophile
Is a nucleus lover. It's electron-rich, often with a negative charge like OH, and it donates an electron pair to attack an electron-deficient atom.
So electrophiles get attacked, nucleophiles do the attacking.
In a nutshell, yes.
Okay, let's just quickly run through the main reaction types.
We can group them. Addition and elimination are basically opposites. In addition, 2 things become 1, usually by breaking a double bond.
And in elimination, one big thing splits into 2 smaller things, often forming a double bond.
Precisely. Then you have substitution, which is just a simple swap. One atom or group is replaced by another.
And hydrolysis.
That's just breakdown by water.
Okay, and finally, oxidation and reduction. We use shorthand for those.
We do. Oxidation, which is often a loss of hydrogen or a gain of oxygen. We just represent the agent with O. And reduction, the gain of hydrogen or loss of oxygen, we use H. It's just a way to simplify balancing the equations.
Wow. Okay, that is the entire foundation in one go. It really is a gateway chapter.
It is. If you can handle these core ideas, the naming, the 3 types of hybridization, the different isomers, and especially that carbocation stability, you have the toolkit for the whole field.
It's about getting that dictionary down perfectly.
Yeah, it really is.
So what does this all mean for you? It means you now have the conceptual map to navigate everything else in organic chemistry. And here's a final thought. We know that a simple formula like C4H10 has 2 structural isomers. The formula for decane, C10H22, has 75. Now imagine the mind-boggling complexity that arises when you start adding functional groups into those longer chains. How does that molecular landscape just explode in variety?
It's almost infinite.
Thank you for joining us on this deep dive into the foundational language of organic chemistry. Keep diving deep, and we'll catch you next time for the last minute lecture.